So let's discuss question number 54 and 55, the link data question. Okay, so this is from test 5 from IC engine. So thermodynamics, applied thermodynamics, guys. A gas engine running on Otto cycle. So let's draw an ideal Otto cycle in a PV diagram. So let's say it starts here. You have a compression and then constant volume heating, then expansion from PDC to TDC, and then exhaust, which is again the heat rejection. So 1 2 3 4. Okay, so this is isentropic compression, this is isentropic expansion. Okay, and this is constant volume heat addition which takes place at TDC. So this is TDC, this is BDC. This volume let me call V1, this volume let me call V2. Okay, and the compression ratio is defined as the maximum value, the ratio of maximum value in the cylinder by minimum value possible in the cylinder. So that is volume at BDC by volume at TDC. Okay, so that ratio is given as 6. And so now obviously when you compress it, your pressure and temperature rise, and when you supply the heat, temperature and pressure will rise at constant volume. So at this point is the point where you get peak temperature and peak pressure. So let's first find out peak at this point. So what we know is, we know P1 which is 1 bar, and we know T1 which is 27 degrees Celsius. That's it, we don't know anything else. So we know, let's apply for the process 1 to 2, which is isentropic compression. So because we are interested in the 54th bit first, so let's first find out the temperatures. So in isentropic compression, the state, the pressure and volume behave in this way, the temperature and volume also behave in this way. So this is how it varies. So let's, because we know how the volumes vary, we know the ratio of the volumes at 1 and 2. So let's apply this second equation. So T2 V2 gamma minus 1 is T1 V1 gamma minus 1, and gamma is the specific heat. So T2 by T1 is V1 by V2 gamma minus 1. V1 by V2 is 6, by gamma is 1.4 minus 1. Okay, so T2 is T1 27 plus 300 plus 273, so it becomes 300 into 6 per 0.4. So this value becomes, 300 into 2.05, so it becomes 342 degrees Celsius. So this becomes 342 degree Celsius is the temperature at point 2. Now I want at 3. Okay, so but it's constant volume heat addition, and we don't know how the pressure varies, and we don't know how the volumes vary, but what we know is CV is given, and the heat that is added is given. So heat that is added will just, if you apply first law, so heat that is added is change in internal energy plus work done. Work done is 0 because no volume change. Okay, so delta U for an ideal gas is mCV delta T, and M is per kg, so it's 1 kg. CV is given as 0.707 kilojoules per kg. Delta T is T3 minus T2, and Q is per kg 1170. So from this I can get T3, from T2 is already known, so from this I can calculate T3, and the value comes out. So T3 is 1631.8 plus 615, so it comes out to be 2246.8 Kelvin, and if I subtract 273 from this comes out to be 1974 degree Celsius. So this is the answer for 54th bit. Answer is B for 54. Now 55 is the peak pressure in the cycle. So obviously at point 2 and 3 the volume is constant, so if I apply PV is MRT, which I can apply at any state points. From this P2 by P3 is T2 by T3. And do I know P2? Well, I can calculate P2, right? Because P power gamma is constant between 1 and 2. So P1 V1 power gamma is P2 V2 power gamma. So P2 by P1 is V1 by V2 whole power gamma, and therefore P2 by P1 will be 6 power 1.4. That is nothing but 12.28, and P2 is 1 bar, so P1 is 1 bar, so 12.28 bar is the pressure after compression. So 12.28 by P3. P3 is the peak pressure which we are interested. T2. Now T2 is something which we got. We got 342. That is nothing but 615. Remember to convert in Kelvin. If you don't convert, it's wrong. And T3 is 2246.8. So if I calculate, I get a value P3 which is 44.82 bar. So this is the peak pressure, and therefore the answer is D. So just all this cycle problems, Brayton cycle or Otto cycle, just need to know the cycle and each of the process, and then just keep on applying. So thank you.